We at Understand AI believe that AI is maybe the most powerful tool our generation has at hand. And we want to make it accessible for as many companies as possible because we believe the more companies are using it, the better it can unfold its potential. So how do we do that? We are building an automation engine for annotations to provide our customers with the right data at the right quality and the right quantity. And this is so important because curating the data and preparing the data set for an ML project is one of the most labor-intensive parts of the whole project. So this is where we come in, because we believe if we can automate that process, prices are coming down, it's much easier to run such a project, and AI can unfold its potential. So what do? We provide a tool set with our automation engine to actually automate annotations. My talk today, I want to go into what it takes to get your AI production ready. And I believe I can share some thoughts about that because this is part of my day-to-day job to make that happen. So we have a lot of customer projects where we need automation to bring down the prices, and we have a team which is working relentless to get models into production so that they are valuable for our customers. And this requires that you do not only have a prototype, but that you make them actually work. And the question is, how can you do that in an efficient way, so as fast as possible, basically? There are two angles how we look at that problem. So the first is the experimentation speed, and the second one is the real-world performance. So the experimentation speed you need to find the right solution to achieve your real-world performance. But the real-world performance does not come from experimentation speed finally, it comes from the data. So we'll look into that. Let's get started with experimentation speed. And let's get started with a quote from Andrej Karpathy. So he's the director of AI at Tesla, and he knows what it takes to bring AI to production. And one of his quotes was, because deep learning is so empirical, success in it is to a large extent proportional to raw experimental throughput. The ability to babysit a large number of experiments at once, staring at plots and tweaking, relaunching what works. So he nailed it. You need to run a lot of experiments, ideally at the same time, in a structured way, and then you need to grab those which work and evolve those. And this is the way how you can get to your production-grade AI, at least from an infrastructure model point of view. So what does it take to actually make that happen efficiently? So we need to look into hardware. So from our point of view at Understand AI, it is overly important that you're not limited by hardware. And it's easy to be limited by hardware, because if it takes a couple of days to run a certain experiment, but you have some more ideas what could work, but you're not sure about that, you need to run that in parallel, otherwise you're losing so much time. And it's the same if you apply that to customer projects, and you actually have your models running in production, then we have peak hours where we need a lot of GPUs at the same time. And this is where we are using cloud providers, so that we can easily scale up and scale down at any time, and we have built our whole infrastructure around that possibility to scale easily up and down. So what you need to do, if you want to get your AI product into production quickly, you need to be sure you're not limited by hardware and you can scale at any point in time. Then there's another one, it's benchmarking. We actually start with benchmarking first. So we are building our benchmarks before we are building our models. And we learned it the hard way that this is an absolute necessity and it's a requirement to do that. Because if you don't have that benchmark, and if you do not exactly know how you're doing and in which areas of your data processing pipeline you're doing well or not doing well, it's so easy to put effort and time into the wrong part of your pipeline. And in the end, it goes nowhere. So this is why we're starting with the benchmarks. So we're sitting down and we're really thinking about what do we have to achieve in the end and how can we measure that? And then we're putting benchmarks in place, and only then we start with our model with our data pipeline and our models. It's a little bit like test first, we have a benchmarking first approach. Next one is reports. If you run that many experiments at the same time in parallel and over a couple of weeks to find a solution which works, and you're slowly working yourself forward through the problem, right? Then it's easy to lose track, especially if you maybe onboard new people. You do not want to lose your learnings. And this is why we use reports. So we have reports to record our findings and to make them accessible to other team members so that they can look through those reports and see, okay, we already tried this, we tried that, this was the result, maybe we should do something else, or maybe it's worth the effort to look into that again. So this helps us a lot to work forward in a structured way. Then there's the thing with the artifacts. So if you have such a model, and you have trained it and it works quite well, and you have maybe another one, you have trained that one and it works not so good, and then there's a third one. So it's not enough to just have that done at some point in time. You need to be able to pull that out of your pocket at any time. So this is where you need to archive your artifacts. So we have a in-house built solution to do that, so that we have the data set and the train set for every model version. We know what it was, and we can reproduce our work and our results. So we can retrain the exact model on the same data, and then we can work forward from that point onwards. So this is automatically done. This is super important. Otherwise, you easily lose track, and then you have to do stuff over and over again. So that's where you have to make sure that you're well organized and you have your stuff at hand. Then there's the next one, which is the data processing pipeline. When we work on customer projects, it's not that we have a single model which is doing everything. You put in your data, you get it out, and you're fine. So that's not the case, actually. The problems we try to solve are a little more complex. So what we have is we have a series of steps which we process subsequently. And this is our data processing pipeline. And now we learned, if you want to be efficient with such an approach, you need to be able to control each element out of that pipeline individually. What you can see on the slide is on the left-hand side, you see a little bigger flow from a little bit zoomed out. So we have automation flows with 15, 20 steps until we have our end result. And this is part of that. And if you zoom in a little bit, you can see that there are building blocks like that regression, for example. And then you can open them, and then you have a full tool configuration. You can put in your Docker image, for example, and then the system will take care about spinning that up and scaling that down, and running it on the data which goes through the pipeline. But it's super important that you can tweak and monitor and debug every single element out of that pipeline on its own. And this will get you a lot of experimentation speed, because if there's one little thing you want to tweak, you can just go to that element. So it's not the whole pipeline. So you have independent building blocks. The next one is, which directly comes with that, is the snapshots. So if you have such a pipeline and you want to iterate on automation step 3, for example, right? But it takes an hour to run step 1, and it takes 2 hours to run step 2. And you now have a little change in step 3. So it's really annoying if you have to always wait 3 hours until the data makes it until to step 3. So this is why we implemented a snapshot system. And the snapshot system helps us to have a snapshot of every single step of the pipeline. And we can either run a subsequent step on the real data, which is just coming through, or we can run it on the snapshot. And if you want to do some little tweaks, if you just want to check out a new iteration of your code or of your model, you can just run it on the snapshot. You can also do that locally on your computer. So and this saves us tons of time, and is really getting us up to speed and making us more efficient as a team to come up with the desired results in the end. And there's another thing, so it's the shadow mode, so we call it shadow mode. So if you have developed such an automation, and it feels quite good, and you have run it on your validation sets, on your ground truth data, and you get nice results out of it, right? You can still not be 100% sure that it's actually good, because it might just be good on the data you tested it, but it's not necessarily on all the other data which can come through such a data pipeline. So what we do is we have a shadow mode. So this means we're running that in parallel, and since we're doing data annotation, we can always have a team doing something manually, and then we can run our automation parallel to that. And then in the end, we compare the results of both of that. And if the results are good enough, we can scale down the manual team and we can scale up our automation, and then we can run the data through the automation. And this is how we achieve a higher automation rate. And we can then be sure that the quality is actually where it needs to be. It's not such a black box anymore because we can test it out on the real data. So, and the learning out of that is, so infrastructure is your backbone. So you need to put a lot of effort into your infrastructure to make sure that it's reliable, that you have the performance you need, that you can debug it, that it has all the capabilities you need. And this is all part of that infrastructure part. And unfortunately, it's not like with classical coding, so that you can just come in and use the best tools on the market and you're already in a perfect environment. So that's typically not the case with those AI projects. There's a lot more because it's much younger. There's a lot more which can change and where you have to come up with your own solutions. So that's why it's so important to have a solid infrastructure to solve your problems at hand. So we put a lot of effort into that because this is what finally gets our experimentation speed up, so we can much quicker come to the desired solution. Now let's talk about a little bit about models. So our algorithms. Actually, we typically start with out-of-the-box algorithms, like I like to say. So, for example, Papers with Code is a good web page where you can find models which might be suitable for your problem. And then we take those models, those out-of-the-box models, we put them into our job runners, we make them run within our data pipeline, and then we find out what is the baseline performance of our automation pipelines if we employ those models. And then we start to learn what we actually need to solve our customer's problem. And if it turns out that it's the model which is the limiting factor, then we're going all into the model. Then we're coming up with our own architectures and all that kind of stuff. But quite often, it's not necessarily the model, it's the post-processing. It's maybe the tracking, or it's some other stuff which is not working, or which is the limiting factor, where we have to invest first because before we're coming back to the model. So that's why it's so important to have that benchmarking in place, that you know where to put your time. So, but get started with out-of-the-box models. So that's our recommendation. Get as quickly as possible your pipeline up and running, and then see where you actually have to put your effort. With hyperparameter tuning, so once you're settled on a model, and once that model is good and you believe you have to tune it a little bit, and you're going into the hyperparameter tuning part, then our recommendation is use tooling. Use tooling to get that part structured, because also here it is very easy to get lost. And we are using, for example, from weights and biases, we are using the hyperparameter sweeps, so to get our models tuned and to make them work better. So this is really, really helpful in that case. And then there's one other thing which might be obvious, but it's worth mentioning it from my point of view. It's super important that you can visualize all the different parts of your pipeline, so that you can look into the results when they're coming out of the pipeline, that you get the required information visualized, and then you can assess the performance, you can get a feeling for that. And if you're all trying to do that within a black box and not looking into that, it's really super hard. That's why we have our in-house visualization tooling, to make sure that we can actually see what our models are producing. So our recommendation is, don't spend too much time on the models in first place. So I know it's really easy to get into that one, and that's maybe the most attractive part of such a pipeline, to play around with the models, to come up with new architectures and to try out stuff. So that's really fun. But the thing is, if you want to get it into production and if you want to make it work, that's not necessarily the best part to spend most of your time. So it's much better to get up your pipeline, to have your benchmarking in place, to know where to put the effort, and then to start playing around with your models if it's really required. All right, so this was for the first part. This was all about how do you get your experimentation speed up. And now we're looking into the performance, because if you can experiment a lot, that's fine. But what you ultimately want to achieve is that real-world performance. So how do you get to that real-world performance? And here I want to talk a little bit, give a little bit of a background. So in our case, when we're working, there's typically that fixed performance, I call it. So it's easy with machine learning or with AI to come up with a prototype which is kind of impressive or which can wow you, right? But this is nice, but it's not really helpful, because the thing is, it needs to be super reliable. So think about when you're trying to dictate a text, right? And it's easy to impress you with the ability of a phone to translate your voice into text. But if you then use that and you have to correct every second word, then it's super fast, it's super useless. So it's much faster to just type in the text. And this is this potentially usable, how I call it. So you need a super high performance of your model in all circumstances to really make it usable. And this is the fixed performance thing. So if you want to have it work in real world, you need to achieve that performance level. And now the question is, how do you do that? So again, Andrej Karpathy, he had a couple, I think 2 years back or so, he came up with that one. So he said when he made his PhD, his main thought went into algorithms. So how can I optimize my algorithms? But when he went over to industry, when he changed, then he said, well, now the most time I spend on thinking about data sets. So why is that the case? So when you look into academia, so you typically have a fixed data set. And it's important that you have a fixed data set, because if you're operating on the same data set, you can compare algorithms and architectures against each other. And you can say, okay, this one works better than that one. But the thing is, you want to be better than the competition with your algorithm. But that's also sufficient. Let's say you have a complex problem to solve and your algorithm is giving you 61% performance, and the other algorithm is giving you 60% performance, then the one with the 61 is obviously better, so you made the race. But the thing is, you cannot use that in production because it's not good enough, so it's not really helpful. But it's totally valid to have that when you just want to find out what is the best algorithm. But if you move on and you want to deploy it to a customer, and the customer should be happy with that, and you want the customer to be happy, then it's the other way around. So you have a fixed performance, what I talked about. So you need to reach that threshold of those 95, 98%, right? And the model, well, I mean, who cares about the model, right? I mean, as long as you achieve a performance, you don't care what model it is. But how do you do that? It's the training data, and that's the thing. So it's a variable, ever-changing data set, and this is where the performance comes from. I mean, of course, you need a suitable algorithm, and there are differences between the algorithms, but you need the data, because from the data, the algorithms learn from the data, and that's how you get to your performance level. So you have to look into the data. So the data is the important part. And this is why we say data defines everything. So data defines how good your model actually performs in a real-world scenario. This is also a paradigm shift. In classical software engineering, you have an explicit code which solves a problem, which directly solves a problem. But in this case, you're moving away from that. You're getting into a direction where you have a general code. It's the algorithm and of your machine learning model. But you teach this algorithm with the data you feed in. So this is a totally different approach, because now it's so important to maintain your data set and to keep your data set up and to make that representative for a real-world problem and a real-world variety. So this is what you're doing. This is totally different from the classical paradigm of software development. And so this is why some people call it software 2.0. Now let's look into that data thingy a little bit. So let's start with the characteristics of data. So there's the data quality thing. So when we talk about data quality, we typically do not mean the sensor quality. So like photos, for example, LiDAR scans or noise recordings or something like that. We're talking about the quality of the labels we have. So in that case, you can see you can see a data set which is called VOC, and there's that motorcycle doing a wheelie on the left-hand side, and you see those bounding boxes, so those square things. So these are called bounding boxes, and they're annotating and describing what's on the picture. So there's one for the motorcycle, there's one for the rider, there's a couple others for the cars. And what we now did is we applied a small noise to that data set. So that on the left-hand side is the perfect one, it's called ground truth. In the middle, there's a small noise applied. So you can see that the error, the little error is pointing to the left hand of the car, so it's a little bit loose here. And on the right-hand side, there's a large noise applied, so everything is a little bit loose and not only a little bit. And what we wanted to do is we want to have the exact same algorithm, but train it on all three data sets. So the ground truth data set, the small noise data set, and the large noise data set. And the goal was to figure out how important is it to actually have a good labeling quality with tight boxes. So the precision is very high. And we ran that algorithm, and it turned out that at an IOU of 0.8, an IOU, by the way, so that's intersection over union. You're taking two boxes. This is one box, and this is the other box. And if you put them above each other, it's 1.0. So that's 100% coverage. But if you move them away, so then your percentage is getting down. And in industry, typically you want to achieve something around 0.8, so that would be considered as good. And so if you now run the algorithm or train the algorithm on the different data sets, you can see that there is a 40-point decrease in performance if your labeling quality is not good enough. So it's super important, depending on your use case, that you have precise labels. But you also have to be a little bit careful about that. So it's good. So know your problem, I keep to say, because there's a couple of use cases where you don't need that precision, right? So if you're talking about scenario extraction, for example, or just the validation use cases, there's a totally different set of precision required, not the box precision, for example. So you can lower your cost of annotations or of your data set preparations if you know your problem and if you adjust your quality requirements to your problem. So this is super important. Then there's the thing with the quantity of data. So in general, you can say the more data, the better. And the reason for that is simply that your algorithms can see more objects in a higher variety of circumstances and then learning from it and getting more and more robust. So that's the reason. And in testing on different data sets with different sample numbers, fine-tuned or not fine-tuned, we always come to the result that you get you achieve better results if you have more data than if you have less data. Now let's talk about typical data distribution and the problem which comes out of it. So if you're driving around with your car, for example, most of the time you're not ending up in critical situations, and you're also not ending up in questionable situations, so edge cases in that case, where you're not really sure what to do. That's the normal scenario. But if you want to train an AI which really reliably detects your environment and knows what to do even in critical situations, then this data distribution is not really helpful, because if 90% of the data is normal driving, but you need exactly those edge cases in critical situations, a lot of those 90% of driving is simply worthless, or in the other words, it's super hard to come to a data set which has enough critical and enough edge cases. And that's the problem with the data distribution. And we at Edge Cases, this is an example taken from one of the dash cams you sometimes see in the internet. And yeah, if you want your car to behave nicely in such a scenario, you need to teach it how to do that. So you need to see that situations. And out of the data you collected, you then have to build a balanced data set. And this balanced data set needs to come with an appropriate number of critical cases, edge cases, and normal driving situations. And compared to the real world, this is totally unbalanced, because you need a super high amount of those criticals and those edge cases, and it's much higher than what you would see in reality. And this is why you have to collect so much data, so that you're finally able to extract the critical and to come up with such a data set. And this then, from the algorithm's point of view, is actually balanced, because it now can learn, or it now learns how to behave in such situations, and is not always overwritten with standard scenarios or with standard situations. And to do this in a sufficient way, you need data selection, and you need tooling which helps you with data selection. So what you see on the screen here, this is a data selection tool from IVS. It's called IVS from Intempore. And here, for example, you're getting your recordings in, and you can classify those recordings for with geo coordinates, for example, and you can say, okay, give me data from that roundabout. And you can say, okay, give me data from that roundabout in that weather situation. And then you can dig deep into your data and can build a data set in a structured way. And if you go back to the slide before, so you see this construction zone and traffic lights and overtaking, and this is just a really, really small subset of what you would have to collect if you actually want to build self-driving cars, for example, right? So there's many, many more categories, but for each of those categories, you need the edge cases, the critical cases, and the normal driving scenarios. And this is why you have to be super organized with your data selection approach and with composing a data set which actually represents the real world, but not represents not the real world, not in the sense of that real-world data distribution, but in a way that your algorithm can learn from it. And there's Jan LeCun, and he's the chief AI scientist at Facebook. What he said, I'm starting to find it annoying when people say your algorithm is biased. When what is actually happening is your data set is biased. The algorithm is doing the right thing, given your data set. And this is exactly the point. So if it's not in your data, your algorithm cannot learn it, right? Or if the critical situation is underrepresented in your data, the algorithm might forget it and might override it with the normal scenarios and the normal situations. And then even if you showed it to the algorithm, but not in a sufficient way, right? Then your algorithm cannot really learn from that. And this is really problematic. And this is why it's so important that you build up a representative data set, which actually trains your algorithm in the way you need it. Let's talk about training and validation data a little bit. So there's typically a data split, a best practice data split. So they tell you, okay, you have your train set, and then now split it in 70-80% for the train set, and you take another 10 to 15% for the validation set, and another 10 to 15% for the test set. And of course, this is perfectly fine. This is best practice. This is what you would do in academia, right? The thing is, if you have that set, and even if you did everything in the right way, a satisfying run on the test set does not guarantee for happy customers, because it does not necessarily mean that you have covered real-world variance and that your algorithm is performing the right way. So, and this is what you see on that slide. So what if your data set only covers a very small portions of the real-world variance? Then you have to be super sure that your algorithm is not running in this purple section of the real-world variance, but only in the blue one, and this is maybe impossible, right? So, and that's where the validation effort comes in. So the required validation effort to make sure that your algorithm behaves in a nice way. And of course, it depends on the use case. So let's say you're doing something where not a lot is at stake. Maybe it's a little bit inconvenient if your algorithm fails. Well, I mean, okay, then best effort should do. So don't go crazy in validation. But let's think about a situation where you maybe have financial risk, or you're risking fatalities, or you have a health risk if your algorithm goes wrong. So then you have to validate the hell out of it. And yeah, and this is what happens with autonomous driving as well, because there you have to prove that you're as good as a human driver in the end. And this is super tricky. And our recommendation is, make sure that you understand the size of the problem you want to solve, and then start planning accordingly, because it might be much bigger. And if it's much bigger, it means that you need much more effort, much more money, a much bigger invest to make your problem work. So better know upfront how big your problem is. And now we're coming to the last part. If you're really talking about the big problem you want to solve, you need a data engine. And the data engine is something which boosts your data collection. So this is a structured way to collect data, but it's not only a structured way, it's also an automated way to collect data. So let's look into such a data engine, how it could look like. So we're starting in the middle. So there's a blue one, there's a blue section on the left-hand side, a green section in the middle, and then there's the yellow section on the right-hand side. We're starting in the middle on the green section, and exactly in the middle box, and it's to source samples. So you would start to source samples to get raw data. And the next step would be to enrich your data. Enriching data means you describe what's in the data. So there's a box which is a car, and then there is a motorcycle, and there's a pedestrian, and so on and so forth. And then, of course, you do a split. We already talked about a split. And you use some of that stuff to train your model, and you use the other stuff to validate your model if it works afterwards. So then you do your retraining, or you update test management on the right-hand side, and then you run your model, or you validate your model. So that's the two things. And then now the interesting part starts. It's the identify misprediction, and then you go to source additional samples. And if you do that often enough, then you might end up with the perfect AI. And let's look into that data selection piece. So data selection is a key technique to keep the data flow under control. So source samples means you have to select your data. This is what we talked about before. Make sure that you're sourcing the right data. And most of the time, you need to build your product around that data sourcing. So make sure that the users of your product help you to source the data. So this then is a reliable way to get more data and to get exactly the data you need. Once you mastered the sourcing of samples, the next step would be that you add the samples to your train set, and you add your samples to your test set. When you add your samples to the train set, you need to make sure that you keep the right balance. So we already talked about a balanced data set, and if you add new samples, it might mean that you have to add additional samples to other categories as well to make sure that they are not underrepresented suddenly, right? And so this is why you need to keep track on that, and the more different scenarios you add, so the more you also have to add to the rest of your data set to make sure that it stays in that perfect balance. And on the other hand, when doing your validation, you need to aim for coverage. So here the balance is totally different. You just make sure that you have a high enough coverage of the weirdest cases you can come across, and to put them into your validation set. So here you need a different type of balance in that case. So it's more coverage than being balanced. And in the end, the data needs to cover the real world variance. So we already talked about that. And finally, there's the identify misprediction. And this is really a tricky one, because you need to find out, ideally in an automated way, where your algorithms fail. Because this helps you to then come up with the next set of data, which then hopefully improves in that area without making other areas worse. And what you also have to keep in mind, the initial data will not cover the real world variance. So only over time you will come to that coverage. And what you also have to keep in mind, there might be model staleness. So if the model is fine today, it might not be fine tomorrow anymore, because the world changed. So you have to retrain that. You have to make sure that it also works nicely tomorrow. So this is an important thing not to be forgotten. And in the end, it is about to design the product in a way that it makes end users label your data. So this is what you need. For example, a super nice example is when you have those recommendation engines somewhere in web shops, because there people are putting in a text describing how they feel, and then they're putting a star rating on top of the text. And now you can nicely correlate that, and you can learn from that. And so the people give you the data. So the product is designed in a way that you as a developer get the data you need to get better with your algorithm. So, depending on the size of the problem, you'll need techniques to cope with a constant raw data stream to bring your AI to perfection. And this is what the data engine is about. So you need to make sure that you're getting the right data you need. All right, we are now at the end of my talk. Let's come to a quick conclusion. So first of all, you need to aim for experimentation speed so that you can run as many experiments as possible. And then you need a rock-solid data acquisition strategy to make sure that you actually achieve your performance. Because if you've figured out how your model needs to be structured to perform on that problem, then you also need the data to train it so that it can learn how to behave. And only if those two things come together and you are very structured and efficient in both areas, then you can quickly deploy results to production which actually make customers happy. And don't forget, data defines everything. Thank you very much.